Hello, today we're learning about spectra. So for a start, what is a spectra? It's what you get when you have light and you split it up into its components. So if sunlight hits raindrops, splits up, you get a rainbow, right? You get a continuous spectrum of all the colors from violet all the way up to red, and even all the colors you can't see. So on the left of violet is the ultraviolet, on the right of red is infrared. Um, and the first dot point here asks you to examine spectra from a few things, from discharge tubes, reflected sunlight, and incandescent filaments. Important that you don't look directly at the sun. Now, how to see the spectrum and what will they look like? Well, for a start, sunlight will probably look like the continuous spectrum, although if you have very fine instruments, you can actually see some detail inside the spectrum as well. But if you look at incandescent filaments or discharge tubes, it will probably look more like this one down here, the emission spectrum. And the explanation for that is that different types of atoms, they will emit only certain colors of light. So these ones here are for hydrogen atoms. So a hydrogen atom will emit these particular colors of light and not all the colors in between. Okay, and so that's what it will look like if you use an incandescent filament or a discharge tube. Okay, so how to actually see them? You'll use probably a spectroscope at school, or if you have a diffraction grating, light that goes through a diffraction grating should make a spectrum. You might not be able to see it with your eyes, but a phone camera can usually pick it up. Or you can build your own spectroscope. To do that, all you need is a box, and inside the box you have a CD, and a CD can act like a diffraction grating. It's a CD that you've got to be willing to not care about. You have a little hole at the top. This hole is for light to go in. You have a hole on the side here. That hole's for light for you to see. And what happens is that the light, you point this hole at the top at what you want to look at. The light comes in, bounces off the CD, and goes into your eye. And when it hits the CD, it splits up into the spectrum, and you can see the whole spectrum. Very simple spectroscope to make. Now, I said before that this down here is the hydrogen spectrum. That is all the colors produced by hydrogen. It will also absorb those same colors. So if you shine all the light at hydrogen, it will absorb those particular lines of light, leaving behind everything else. So you can talk about either the absorption or emission spectra. This is really useful in the identification of elements, because every type of element has its own particular lines that it will absorb. It's kind of like a fingerprint for that element. They don't really have fingers. What I mean is it's a unique thing that we can use to identify them. This one is for hydrogen. If you get different lines, you've got a different element. So particularly for stars, we can use this information to learn about their chemical composition, because when starlight comes to us, we can put it through a spectroscope, we can see what lines are produced, work out what they're made of. Turns out it's mostly hydrogen, quite a lot of helium, and then a smattering of lots of other elements in stars as well, depending on the star. However, we can use the spectra of stars to learn about these other things as well. Let me put my spectrum to the side for the moment. Let's get that over here. Okay, boom. This is called a black body radiation curve. We've got temperatures here. So 5,000 degrees Kelvin, that's about the temperature of the surface of our sun. And what this line here is showing us is all the different wavelengths, or I guess the spectra, produced by our sun. So it's got a lot of visible light. Visible light is by far the most intense source of light from our sun, and then it drops off. So we don't have much in the gamma ray, we don't have much in the radio waves, and we've got a bit of everything in between. So for a start, and you'll see that if it was a 4,000 Kelvin object, then it peaks around red light rather than in the middle of the visible spectrum, and so we'll have a reddish, a whitish reddish color to it. If it's 3,000 degrees Kelvin, it's peaking in the infrared, so If you put your hands near it, you'll feel that heat. It's also still producing some visible light. And if it's 2000 degrees Kelvin, really the only visible light it's making is orange and red and a lot of heat. So it will look red or orange. You won't look white at all. And you can imagine if you holding a piece of metal inside a flame, and it heats up and it glows. First it will glow a dull red, then it will become a more whitish red. And if you could heat it up enough, it would turn pure white, or look white, like the sun does. So by looking at the color of a star, like our sun, you can learn a lot about its surface temperature, because the colors being produced by the sun tells you what temperature it is. But small shifts in the color can tell you other bits of information. So to learn about its translational velocity, you need to know a bit about red and blue shift. If an object is moving towards you, any light that comes off that object is going to be squished, the wavelengths short. Any object moving away from you, the wavelengths get stretched out. This is called the Doppler effect. It happens with sound waves as well. If you've got an ambulance or something passing you on a street, as it comes towards you, the sound waves are squished, sounding higher pitched. As it goes away from you, they're stretched out, lower pitched sound. So any stars that move towards us, we can see that this curve shifts towards the blue side, right? And we call that blue shift. So instead of the curve where it is, it's going to be just a little bit to one side. Yep. Or if it's moving away from us, it gets redshifted and the curve ends up a little bit on the other side. So now you might think, well, okay, if the curve's a bit more to the blue, how do I know it's not just hotter, right? You said before that this red one here could just be colder object. We have a medium temperature object and then a hotter object here. What you need to do is you need to combine the colors with the spectrum. So you know that the hydrogen spectrum is going to fall in a particular spot along here. If that hydrogen spectrum is shifted up or down, that can't be because of temperature. Temperature is not going to shift the position of the hydrogen spectrum. It can only be because of the velocity of the star itself. So if the star's moving, say if the star's moving away from you and it's being redshifted, that means that these lines are going to be moving across. This line here is going to move across to here. This green line is going to move across to here. These bluey, purpley lines are going to move across as well. They're all going to shift slightly. If it's moving towards you, it shifts the other way. Okay, rotational velocity is a bit of a strange one. If you imagine the sun, shouldn't be too hard to imagine, and the sun is rotating around like this, the parts of the sun on this side are moving towards us, and the parts of the sun on this side are moving away from us. So the parts moving towards us will experience blue shift. I'll put some blue there for you to remember that. And the parts moving away from us should experience some red shift. So what we get in our spectrum is we get some movement to the right and to the left. The line actually moves both ways and it spreads out. So we get thicker lines when the star is spinning. The faster it's spinning, the more exaggerated these velocities are, and the bigger the blue and red shift, so the more that line is spreading out. Now, still not so simple, because we also have density. And the more dense the gas is at the surface of the sun, that also has an effect on the lines. It also spreads the line out. So we need to combine all our bits of information together. We need to combine the temperature, because the temperature gives us an idea of how much light intensity should be coming off it. Okay, if we can see how much intensity of light, that tells us the temperature. If we know that at this certain temperature that the sun is a certain size and it should have a certain density, then we know that if the lines are spread out, we know that's because of rotational velocity, not because of density. However, if we have a If we have a very large star, which we know should have low density at the surface, so you have a very large star, very low density, and we have spreading out of the lines, we know that's due to density, not due to translational velocity. We need to combine these pieces of information together to learn about stars the best. It's complicated. That's why there's a whole field, astrophysics, dedicated to doing this stuff. But this is the best way that we can study our universe without actually going there. At the moment, it's impossible to visit any star other than our own sun.